Okay, hi everyone. Nice to meet you. My name is Yuval. I'm the CTO at Rift. At Rift, we are an Iceberg management platform, so we help with Iceberg management, smart compaction, and things like that. So I'm here to talk to you about a topic that's dear to everyone's heart here, which is streaming. And thanks you for the great talk before, and I'll dive more into compaction with streaming today. So tons of streaming tools have been added along the years, and it's easier than ever to stream into Iceberg. However, the problems are just getting harder and harder. So let's talk about the hardest problems today in Iceberg and streaming. So a 60-second intro before that, just so we're on the same page. In Iceberg, when we're streaming, we either are inserting or merging records. So when we're inserting, every snapshot we create in Iceberg creates all of these files here that you see. So every snapshot will have a metadata JSON, a manifest list, manifest files, and data files. So a lot of files for, imagine this happens every tick of the stream. So every 10 seconds, every 15 seconds. Same thing for merges, but actually even worse. Because if you're merging and you're overwriting data, then you get also deletes files. So some of the files you left before are no longer valid. So what are the challenges with dealing with streaming in Iceberg? Three are the hardest problems: small files, active storage, and merges. Let's talk briefly about each one of them. Small files. The problem is very easy to understand, right? Tons of small files created by a very high-performance streaming coming into your Iceberg. This creates higher costs, very bad latencies in query planning, and very bad latencies in data read. You can imagine what the query engine has to do only to get a very simple query from Iceberg, where it has to go through all these manifests, then go through all these data files just to get a simple query. So what do? As we said before, compaction, right? Compaction, very simple. Take 100 files, convert them into one. Apparently, this problem is much more complicated than it appears on the surface. It's easy to take these files and convert them to, in this case, 232 megabyte files. But what happens in streaming? So let's take two examples. Two different compaction strategies on a streaming workload and see what happens. On the left, we wait 10 seconds or 100 seconds if it's 10 seconds of a tick in the streaming. We have 10 files of 1 megabyte each, and then we compact them into one bigger file of 10 megabytes. How many bytes did we compact? 10 megabytes of bytes. That's perfect. Let's see on the right. Now we're not waiting as long as on the right side, on this side. We're doing it every 2 ticks of the stream. So we're taking 2 files, we convert them into 2 megabyte file, and then this 2 megabyte plus this 1 megabyte becomes 3, and so on and so forth. So what did we achieve here? We have a much better SLA because we don't leave a lot of small files on storage. But if you count the number of bytes we compacted, we actually have almost 5 times more bytes compaction. So now imagine this is a petabyte scale data lake. That could mean a 50K bill of compaction versus a 10K bill of compaction, right? So two different strategies result in a very different cost and efficiency. So how would you measure compaction? If you want to measure your own compaction in your own Iceberg Lakehouse, I would look at 2 things, right? How much does it cost? And then how many small files were read? And I think these are the ones that you want to optimize, right? So the number of small files you're going to read is really dependent on how much time do you query from that table. Do you query data from right now, or can you wait a day until you compact? And if there are tables that you don't necessarily query every day, maybe they don't need to be compacted at all, right? As opposed to if you do query them a lot, then you have to spend a lot more money on compaction, but that would result in better performance for your queries. So these are the 2 axes that I would look at when measuring compaction. A few considerations is when to compact, what to compact, and something else is how to compact, which I'm not going to talk in this talk today. When to compact is basically when to run, or even, as I said before, when not to run. You can either do it commit-based, file-based, or interval-based. So you can say, I'm going to compact every hour or after every 100 commits. And each of these strategies work for a different use case of your data. And what to compact is important as well, right? You can have Let's say you want to define a budget for compaction. You don't want to get overboard. Then you have to decide, okay, which tables are more important for compaction and which are less. Same things go inside a resolution of a single table. You want to decide which partitions are more important to compact. It's much more important to compact if it's a time-based partitions table, much more important to compact the last day than a year ago that nobody even queries. If you have late arriving data, that's also something that you have to take care of, because if you have data coming in from 3 months ago, do you go back and recompact the data or do you leave it aside? So these are some important compaction considerations. The next issue would be active storage. Active storage is a metric that you can define by counting the size of the current snapshot in Iceberg, how much data does the current snapshot take in gigabytes or terabytes, versus how much the entire Iceberg snapshot tree, including all of the time travel that you're keeping, is taking. Or even you can take it to the next level and compare it to the entire size of the bucket at all. Now, why would these two numbers be different? They're supposed to be really, really close. Let's see what streaming does to a table that makes this really, really bad. So here's the streaming situation with Iceberg. We have two 1 megabyte files that are written, and then we compact them to 2 megabyte. Another 1 megabyte is written, we compact them to 3, and so on and so forth. Now let's look at the latest snapshot. This is what your users are querying, right? This is what you think you're paying for. What we have here is 4 megabytes of storage. And again, imagine this is 4 petabytes, not megabyte. But essentially, because you're saving all of this time travel, what about these files that are still here that are no longer relevant for your users, but you're actually paying for them, right? So in this case, we actually have 9 megabytes, so basically a 44% of active storage. That means that if your S3 bill for that table is 100K a year, it's actually, you're just using 50K of that, right, for your users. Another 50 just goes for files that you compacted and haven't really deleted, right? And in streaming, this happens, if you only had an append-only situation, that would never happen because all of the files in the snapshot tree are relevant. But in compaction, you just leave unused files behind. So how to solve that? Basically, in streaming situations, you would have to apply a much more aggressive retention strategy, right? Everyone have their own default of retention of 5 days. 5 days sounds like a good idea. But actually, if you use something like Kafka, Rising Wave, Kinesis, all of these services, you're going to get a new snapshot every 10 seconds or 15 seconds or 1 minute, depending how you configure that. That means over 5 days, you're saving tens of thousands or hundreds of thousands of snapshots that are taking up your storage with compacted files that you're no longer using. So using a time-based strategy in streaming situation is actually probably the wrong idea. And you have to use either an absolute number or something much more aggressive, and basically just monitor this number. So this is the second biggest problem in streaming. The next one would be merges. Everyone, if you look at the Iceberg Slack, everyone has problem with merges performance in streaming. It's very slow. Nobody knows exactly what's the magic solution. And there is no magic solution, but there is a few things to consider. So this is how a merge looks like. And the problem with merge is it's not just a write query, right? It's also a read query. And it's two queries at the same time. So you're searching for data and then you're replacing it. One thing that's cool in Iceberg and the latest versions in Spark is SPJ or storage partition joins, which basically allows you to say to an engine like Spark, hey, Iceberg has already partitioned the data. So I have already partitioned it by hour or customer ID or something like that. When you go and merge that data with new incoming data, don't reshuffle the data between nodes. Just keep them where it is. Allocate each node to a specific Iceberg partition, skip the entire shuffling between nodes, and gain much better performance. So this is basically how it looks like with SPJ versus without. And make sure if you're doing merges that you're configuring SPJ to work correctly, and that your merge queries are actually correlated to how you're partitioning data on your Iceberg table. The next big thing is, of course, copy and read versus merge and write. Each one of them has a different trade-off, right? If you're doing copy and write, your query engine is much happier because it doesn't have to do any job of merging those files while reading. But it does cost you with a very high latency when streaming because you have to do it every tick of the stream. A better way would be to do merge and read, but then again, you're left with a problem of compacting this data or leaving it to the query engine, which gets us to the previous problems we talked before. So either do merge and read to reduce the latency, but then have a very aggressive retention strategy and compaction, or use the copy and write. And lastly, commit conflicts. Everyone that are streaming and doing compaction at the same time are suffering from commit conflicts. And again, there's no magic solution here, but when scheduling compaction, you want to make sure you're scheduling it correctly to not interfere with your streaming, or at least have your catalog be aware and prioritize the commits of the stream against the commits of the compaction. A few takeaways. So don't be afraid of streaming with Iceberg. It actually is, it works very well. Tons of companies are doing it today, but be aware of the 3 problems. Small files, very low active storage, and how to merge efficiently. For compaction, measure how much small files are read against how much it costs for you to increase the compaction strategy. If it costs too much and you're not reading less files, you're not doing a good job. And in active storage, first of all, measure this number, and after you have this number, make sure it's above 85% more or less. Otherwise, you're probably not, you're retaining too many snapshots of too many unused files. And when you merge responsibly, choose the right strategy, and apply SPJ. Thank you so much. Any questions? I think we have 3 more minutes for questions.
All right. Questions, anyone? Okay. Going once, twice.
All right.
2.1, 2.2, 2.3. All right, cool. Thank you.
Thank you so much.
Really appreciate it. Thank you very much, everyone.